Alright, so having looked at stability as a criteria in FDTD, the next thing that we want to look at is accuracy of electromagnetic field propagating in the E grid, YEE grid. Okay, so under accuracy considerations, we will pose a very general question. So, for example, if I ask you this, what do you understand by dispersion? What is the first thing that comes to your mind? Frequency dependent, right? So, in a very practical sense, what happens? Different frequencies travel with different velocities, right? So, different frequencies travel with different speeds. Okay. So, this everyone knows is a physical phenomena, right? This is the reason why, for example, you have a rainbow, because the light is traveling at different speeds and the water bubble, it disperses. Okay. Can there be dispersion numerically? It could happen, right? So, one is physical dispersion, which is okay. The other is numerical. So, what would numerical dispersion, supposing I am trying to model wave propagation through a let us say free space, physically should there be any dispersion? Obviously no, but numerically dispersion may happen depending on how I have implemented FDTD. So, would it be a good thing or a bad thing? Obviously a bad thing, right. So, what we look, so that in general that tends to destroy the accuracy of your calculation. If your waves are traveling at different speeds, whereas physically they should travel at the same speed, then that is what is called numerical dispersion. So, we will explore now under what conditions does this numerical dispersion happen and when does it not happen. Okay. So, that is what we are going to look at. Okay. So, let us first look at the true solution. You will notice in all of these calculations we use the wave equation a lot, right, because it is very easy to handle. So, our wave equation gives us the second derivatives of space and time for the electric field. Okay. And this gives us a solution of the form, we all know this, okay, plus minus kx, right. So, this is a right travelling wave. Okay. Let us call this term over here, what would we call this term over here inside the phasor? Phase, right. So, this is the phase phi. Okay. So, if I ask you, if I want to find out at what speed is this wave traveling, then what is that physically known as? Is the locus of, what is phase velocity defined as? Right. So, phase velocity is the locus of constant phase. Right. How do I obtain this? Right. So, constant phase means phase should not change with time, right. So, I will do d phi by dt equal to 0, right. So, that gives me, the first term gives me omega and minus k dx by dt, I will call it v phase, okay, right, is equal to 0. That gives me v phase is equal to omega by k, okay, and I know that this is going to be equal to c in vacuum. We know this already. Now, the question is numerically what is it? So, what approach should we take? What we did is a theoretical calculation. Obviously, the phase velocity is omega by k, which is c in vacuum. Now, I want to answer the same question, but now on in a discrete world where I have discretized space and time. So, what should my approach be? sit at a point and but how do I bring in the discrete world? Correct. So, I mean this method that we are studying is FDTD, right. So, we have finite differences in time and space and we have a second derivative. So, we should take how should we approximate these things? We should approximate the second derivatives by finite differences and see what kind of relation results from it. Okay. Then we can, for example, in that condition look at the locus of constant phase and see is it speed of light or is it something else. Okay. Now, under what conditions, so we have looked at this before, under what conditions will the electric field be a wave like solution in FDTD? As long as the Courant stability criteria is satisfied. So, when Courant stability is satisfied, my E will be a wave, we have derived that. Okay. So, now let us assume that your let us say alpha, right, alpha which is the ratio of C delta t by delta x, this is less than equal to 1. Okay. So, that says wave like solution is what is obtained, right. Now, what do I do? So, this equation over here, I can add it over here and replace it by what kind of a second derivative can be replaced by a finite differences, right. So, let us do that. So, first is the spatial derivative. So, remember our notation for electric field, it is going to be E n I. N is the time index, I is the space index. Okay. So, what will the left hand side of this equation be? Yeah. So, E n I plus 1, okay, minus 2 E n I, okay, next plus E n I minus 1 whole thing divided by I do not need 2, this is delta x squared. And this is going to be equated to 1 by c squared E n plus 1 I minus 2 E n I plus E n minus 1 I delta t squared. Okay. And this E n I itself is shorthand notation for, remember it is a wave like solution with space and time being discretized, right. So, this simplified expression over here is going to be so e to the j, time will become omega n delta t, right. So, omega n delta t and space will become k I delta x. Okay, this is my E n I. So, what I could do is substitute this exponential term into this finite difference equation. Okay. So, before you do that, you can recognize something that will cancel off from both sides. What will that term be? E n I, I can take common from both the left hand side and right hand side, right, and the rest will be a plus or a minus exponential term correspondingly. So, once I do that, for example, what will I be left with over here? First term will have a I plus 1 into x, the ix is gone away. So, I am going to be left with e to the minus j k delta x minus 2 plus e to the j k delta x divided by delta x square. Similarly, here what will I have? E to the j omega delta t, that is the extra term because I am cancelling off e to the j n, right, minus 2 plus e to the minus j omega delta t right. Does this look like something that can be easily simplified? Each of the terms, right, I have a e to the j theta plus e to the minus j theta, that is 2 cos theta, 2 cos theta minus 2 on both sides. So, that will get simplified in terms of half angles of sine, right. So, I am going to get a sine squared, right. So, what I will get over here, let's write it over here. So, the final expression that I get is sine delta, so sine k delta x by 2 squared divided by delta x squared is equal to 1 by c delta t squared sine squared omega delta t by 2, right. All the other factors are common, they get cancelled off. Okay. So, it is a nice looking expression, right. We did not expect that it will simplify so nicely, but that is what we got. Okay. Now, let us see, first of all, let us first check what happens when I set delta x and delta t tending to 0, because when they tend to 0, I should get the correct solution, right. As I make the differences more and smaller and smaller, I am going to approximate the actual derivative, right. So, as delta x and delta t tends to 0, what happens to this expression over here? So, sine theta tends to theta as theta tends to 0, right. So, what will I get over here? So, I am going to get, so let us look at it over here. So, this is going to become k delta x by 2 whole squared, and the right hand side will have omega delta t by 2 whole squared. So, the fact that 2 squared and all gets cancelled off, the delta x gets cancelled off, right. So, k will remain. So, I will get k squared is equal to omega squared by c squared, okay. And our phase velocity, which was v phase, was, what was the phase velocity we had derived? Omega by k, right. So, omega by k is equal to c. So, in the limit everything is well behaved, because this is giving me the ratio omega by k equal to c, right. So, life is good, this is what we expect. Now, the question is, what happens when delta x and delta t are finite? So, we are still in the Courant condition, right. So, we are still saying that c delta t by delta x is less than 1, but they are finite numbers. I mean, if the Courant criteria is not satisfied, I do not get a wave-like solution, but now I am within the Courant condition, but these are finite. So, will this condition still be satisfied? So, first of all, looking at this expression over here, I can no longer replace sine theta by theta. So, it is going to be what it is, right. Now, no, that is to enforce the, let us assume Courant stability is satisfied, okay. So, can you think of a situation where delta x and delta t is finite, okay, they are not tending to 0, they are finite, still I get omega by k is equal to c. This relation has to be satisfied, you will agree, because you have derived it by discretizing the wave equation. So, this has to be satisfied. Can you think of a relation or a condition where you will get the ratio that, like we got in this case, we got the ratio that omega by k is equal to c over here when I took delta x delta t tending to 0. Can I get the same relation k square is equal to omega square by c squared for finite delta x and delta t? So, you can look at this expression over here. Remember, you can play with alpha. Where alpha is this c delta t by delta x, it is in your hand. Okay, so as a hint, if I have alpha in my hand, that means if alpha, supposing I fix alpha, then I only need to fix one of the two, either delta t or delta x, because they are related. So, supposing I fix alpha equal to some alpha naught, then I just have to specify delta x, let us say, and then delta t gets fixed automatically. Does that give you a hint of for what value of alpha is this relation going to simplify to what we want? The question is clear? Question is clear, right? When I look at this expression, it is not at all clear that omega is equal to omega is equal to c into k. It is not necessary that omega is equal to ck is a solution to this equation. But under one special case it is equal to, yeah. So, just look at what happens when alpha is equal to 1. It is allowed, right. So, then what happens, c delta t is equal to delta x, okay. So, then what happens over here? If I now substitute omega is equal to ck, is it consistent on both sides? So, that value is a solution to this equation, it is satisfying it, right. So, omega is equal to, or we will just write it like this, k is equal to omega by c satisfies the dispersion relation. So, what is the dispersion relation is this one, right. And interestingly, it does not depend on the value of delta x or delta t, right. That is, you would not have expected that to happen. So, what is it saying? That for alpha equal to 1, whatever discretization you choose, my wave is travelling at the speed that I expect it to travel, right. So, if I plot something like this, so what will I plot over here? Let me plot the ratio of the phase velocity to speed of light, okay. So, v phase by c. Ideally, we are simulating vacuum only, so ideally this ratio should be 1, right. So, this is 1, and here what I will plot is delta x, okay, to make it sort of normalized to wavelength, because as the frequency changes, everything delta x will have to change. I will just do this, the wavelength that this electromagnetic wave is going on. So, regardless of, so what should this, for when alpha is equal to 1, what kind of a curve will I expect here? Straight line, curved line, angle vertical to x axis, y axis, 45 degrees, what kind of curve do I expect? Straight flat line, right. Alpha is equal to 1, right. So, I can have different values over here, let us say 0.5, 0.4, 0.3 and so on, right. The discretization is getting finer and finer as I approach the origin, okay. Is everyone convinced about this? By lambda naught, that is the wavelength of the electromagnetic wave, whatever omega, convert that to wavelength, okay. But what happens when alpha is not equal to 1, right. So, maybe I should write this expression once again over here. So, what is it? Okay, we can just have a look at it here, sine squared k delta x by 2 divided by delta x squared, and I have this relation over here. So, that sine term will not cancel off on both sides. Then what will you do? Then you have to solve this transcendental equation to find out what? The relation between, I want the phase velocity. So, I want the relation between omega and k, that is what I want to get at. So, this can be done, it has to be solved numerically, because it is a transcendental equation, right. It can be done, but so I am not showing you the calculation here, it is not very hard to do. What happens is that as I have, one thing is that we know that as delta x and delta t tend to 0, I get the perfect wave behavior, Okay. So, on this graph that I am showing you, as I approach the origin, as I go to finer and finer discretizations, what should happen? What will happen to the ratio of Vp to C? It should approach 1, right? Asymptotically, as I make my discretization finer and finer, whatever be alpha, right? That sin theta can get replaced by theta and everything will get cancelled out. So, I know that everything should somehow land up over here, but as I go to finite values of delta x, as I go to larger and larger values of delta x, what happens is the performance begins to degrade. So, this Vp by C begins to look something like this. This is for something like say alpha is equal to 0.75. Then as you begin to reduce alpha even more, then you will get say alpha is equal to 0.5, and is it because the computation, it has nothing to do with whether it takes less time or more time. It has to do with the fact that the solution to this equation is giving you a certain relation between omega and k. In the ideal case, it is giving you the ratio between omega and k to be C. But when delta x and delta t are finite and not related with alpha equal to 1, then there will be some other value of omega by k which satisfies this equation other than C, and that other than C is coming from here. So, this is what is happening. So, this is your numerical dispersion, right. So, the wave travels slower than C, which we do not physically expect. Physically, it's a wave. I have not even put a medium or a material here. Free space, wave should travel at speed of light. But because I am simulating it on a finite delta x, delta t, and I chose alpha to be less than 1, I have this problem. Okay. So, if we want to summarize, so the dispersion numerically, okay. If I wanted to have a knob to control how bad this, I mean this is clearly an undesirable effect. So, if I wanted a knob or several knobs by which I can keep a control on this, what are those knobs? Say that? Yeah. No, that is numerical convergence. That is once I have fixed my delta x, delta t, alpha, I will check whether the solution is converging or not. That is not what I am talking about. I am saying I know, based on this discussion, I know that my wave will have numerical dispersion. I want to mitigate that effect. I do not want my wave to be numerically traveling at a speed different from what it should physically travel. What knobs do I have in my hand to reduce this effect? Alpha is one thing, right. So, I can check it by Courant parameter. I will come to it. Courant parameter is one knob. Any other knob? Discretization. So, discretization fine and Courant parameter alpha is equal to 1, right. But I am going to put a question mark over here. We will come to why. Okay. But I mean the sort of summary of what I wanted to sort of illustrate over here is that by changing the Courant parameter and by changing the discretization, I can put a check on how much numerical dispersion will be happening in my simulation. Okay. Whatever else happens, you know that if your Courant parameter is less than 1, you will face numerical dispersion. In that case, your only way to beat it is to make your discretization finer, and there is a big price you pay for it. You can't just make delta x small, you have to also make delta t small, and so your RAM memory requirements increases, your computation time increases, everything, right. So